All right, line P1, we're taking a look at learning task 6b at this point. We quit after the first section there. It was about 40 minutes already, so we're going to move on to the next section inside here. We're jumping all the way ahead to this three-wire services because it's an important enough concept that we really want to dedicate some, extra, or not really extra, but some dedicated time to it so that we can kind of go through it. Because this is a really common transformer layout that we are going to go and see, where we're going to go and supply our standard single-phase service, a 120, 240 volt type of system. Now what we're doing in this case is we're using that same transformer that we had before, that 100 kVA, 2400, 4800 to 120, 240 transformer, and we're hooking it up to go and create this three-wire service. In other words, if I take a look at it, I see that I have got my complete 240 volt system that has been connected across the bottom. I'm just going to go and eliminate some of this over here and some of this over here. We're going to come back to those in a second. But I want you to go and take a look that what I have on the secondary side is I have got my 240 volt connection. So I've got here to here to here to here. I've got them in series to go and create a 240 volt system. We know that line to line, we need to have 240 volts inside of a regular three-wire Edison type of circuit. Same with this one over here. 240 volts that we have going across from there to there. The big difference between, the one on the left and the one on the right is just the way that the primary side has been set up. I've got a 4800 volt bus versus a 2400 volt bus, but I see that both of them are set up correctly. In other words, they're both going to generate full values of flux that's going to be cutting through the core and across the other one. This one's the low voltage, therefore it's going to be connected in parallel. This one's the high voltage, therefore it's going to be connected in series off of them. All right, let's go back to what we're doing down here. Once we create the 240 volt connection inside of here, the next thing that needs to happen is we need to go and center tap that. Center tapping is just a term that we use for when we take our transformers and we are going to go and tie it into the very center portion of our transformers. Wetting out some other stuff, we'll get to that in a second. So what I have right now is I have got a tap that is going to this common piece that I have here, the X2, X3. I've got those two tied together, and now I've got this tap that goes down here to this line, which we're going to go and term as being our neutral. If you take a look at it, you see how a connection of a device that goes across from line to neutral, let's just connect a device across here and here, that I could go and run current through my transformer and back down and out to that device, right? We can get a 120 volt device connected onto there from line to neutral. I could also go and connect another 120 volt device across from here to here, which would be able to go and have its power supplied by line over to neutral as well. So we see that we can get our 120 volt systems, and last of all, we should be, fairly comfortable with the fact that we could get a 240 volt system as well that would go and get its power supplied from line over to line like that. This is our standard three-wire transformer connection. Okay, let's talk about what the Canadian Electrical Code requires. We know that we have got a neutral point that has been created over here. It's an actual true neutral because it is going to go and counterbalance the currents, right? If I add the currents inside of my neutral, I'm going to end up with a net of 0, and we'll do some of that addition stuff later on. But anytime that I create a neutral by Canadian Electrical Code, Section 10, what I must do is I must ground that neutral point. So I'm going to go and place an actual connection to ground on that neutral point. We're going to go over grounding and bonding much more in depth later on. But really what we're going to find out is that the reason we ground the neutral over here is to stabilize system voltages, but more importantly because all of my bond system is also going to be tied back to that ground, and then I'm going to be able to deliver all of my current through my ground system. If I get fault current, I want that fault current to come through my system and go back to the neutral, and from the neutral go back into the transformer winding that it came from, either to that one or to that one, whichever one it came from, and because we're trying to develop a lot of current to trip out a breaker. If you don't quite get what's going on with the necessity for the ground, that's all right, because we are going to cover that one later on. You should have covered some grounding and bonding inside of first year, and we'll expand on that yet this year. It's still coming up. Okay. I will be able to deliver the full 100 kVA out of these transformers. However, what I do need to do is I need to make sure that I balance that. I don't know if you have done a lot of panel connections, but when you do your final power up of the system, one of the last checks that you should always be doing is sticking an ammeter around each of your two lines. We're going to go around line 1, we'll stick another ammeter around line 2, and we double check and we make sure that the current is balanced. You should never have a panel where you've got loads of current coming out of one leg and hardly anything coming out of another leg. It is guaranteed to go and run you into problems if we have something like that. This is a overloaded transformer because what I have is I've got a 60 kilowatt load, and the only path for that 60 kilowatt load to take its current through is that transformer over there. Can we develop 100 kVA of power through this transformer? Absolutely, we can develop 100 kVA of power through that transformer. But this winding right over here is going to be overloaded. We need to balance these loads. Always double check. How would I know that I have also got unbalanced load? Would be the currents. If I really went through it, I could figure out the amount of current that I would have inside of each of these. How many volts do I have across here? Well, we know that this is a 12240, and we know that each of these is connected from line to neutral. So if I've got a 12240, power is equal to E squared over top of R. We could go and find the total amount of resistance. We would see we were lower resistance on that one. Or power is equal to my E times my I. Let's go work with this power is equal to E times I for a second, and we're going to figure out what current we have inside of here. Pull up that calculator. We have 60 kilowatts, so 60,000, divided by 120, because that's what we have going across this section right over here. And when I do that, I come out to a total current of 500 amps that I'm going to be pulling through this leg. 500 amps that is going to be going through there. If I go to the other one that we have, the other winding, 40,000, divided by 120, I'm coming out to 333. Amps over here. Now, how many amps were each of these windings rated for? If you go back to what we took a look at over here initially, you know that we divided, we took the 50 kVA, half of each transformer, we divided by the half voltage, and that gave us a grand total of 416.7 amps that they were each good for. So this one here is greater than what it actually is supposed to be carrying. Am I actually delivering a full 100 kVA or 100 kilowatts off of this thing? Absolutely I am. But this winding is going to be overloaded. How do my currents balance out? Well, let's just go and take a quick look. We're going to do a little bit of a current analysis off of this one as well, just to prove where each of our currents themselves are going, and so that we can find this neutral current. What we need to do, if we want to sort out currents, is we need to go and establish an instantaneous polarity. Now, we know that it is AC, so we can just grab any point, and we can go and freeze that. Come on. We can go and freeze that point, and when we do so, that becomes our polarity. So let's say that that's where I've got positive, negative. We know that this is the high voltage. This should be my H1 winding. We know that this same transformer here had an X1. It was a subtractive. Therefore, this point over here would be negative, and this one would have to be a positive. And then going across here through, this would have to be a negative. This one would have to go and be a positive, going across through like that. How does current flow? It goes from positive to negative through a source, and then from negative to positive through a load. So we're just going to go and take this 500 amps that we have going through here. The only path is for it to go and travel through here and into there. So we've got 500 entering over there. This one over here, if we take this, we see that we have got 333, but we see that this coil is going to go and have current going through it in that direction. So I would have to have 333, put that up over here, 333, that is going to go and be leaving from there. Which means that, according to Kirchhoff's law of current, the sum of all currents that enter a node has to be the same as that which is going to be leaving a node. So I'm going to have, if I've got 500 amps that is entering and 333 that is leaving, I'm going to have to go and have the difference, whatever that's going to go and be, that is also going to be leaving from here. You take 500, you minus 333, gets you to 167 amps that we would have coming out of here. So we have 167 amps. That 167 amps is going to be traveling down here where it's going to enter that node. If I take a look now, we can go back to this 333. We see that this 333 is going through here. And if I enter 333 amps into this node over here with 167 amps into this node over here, what I'm going to have is a sum total of 500 that is going to be flowing back out. Our neutral is always designed to go and carry the unbalanced current. If I had a balanced load, I would have 0 amps that would be on that neutral. The lower your neutral current is going to go and be, the better your service is, the more balanced that type of service itself is. And that's what we're always going and looking for. Okay, going back to this here one more time as well. In a lot of transformers, now this one we're doing the hookup ourselves inside of the transformer, but in a lot of transformer there's going to be a pre-made neutral connection that's already going to be done for you, and that one is going to be designated a little bit different. Most cases, if I have got a pre-made one, what I will see is I will see a winding, and then it's just going to go down to another point over here, and we have another winding. They don't usually show the crossover in these types, and I'm going to go and have one of these that is going to be labeled as being my X1. The other one is going to be labeled as being my X2, my low voltage 2. And then this point, my neutral, is going to be labeled as being my XO. Anytime that you see an XO or an HO, but anything that's got that O identifier for a transformer connection, you're always looking at a neutral connection. For a neutral connection, if this was that same type of transformer, what I would do is I would go and take my XO and I would connect it down to the neutral, and then I would go and ground that XO point. Same thing, just they're doing it now with 2 separate windings that we're creating our own neutral, whereas this one here is a transformer that's got a manufactured neutral on it. In most cases as well, the neutral will be bonded to the frame, and you're going to have to remove that. But we'll cover that inside of inside of grounding and bonding later on. For now, just be aware of the fact that a neutral component can exist. We don't always make it like we do over here. Sometimes it already exists. It's going to be designated with that XO. All right. Up next, we've got a couple of figures here that are kind of out of order for what the explanation is. All of a sudden, they jump into this, conditions that have to be met when connecting transformers in parallel. They say, we want to go and connect transformers in parallel, and then they go through a couple of these drawings over here, and we don't really understand necessarily what or why they're doing that until they get to some of these other pictures over here where they're saying, look, what we're trying to do ultimately is we want to go and take 2 transformers and we want to put those 2 transformers onto the same set of buses. This is a very common industrial practice where you're going to go and have a system, and then your system is, running out of power. You don't have enough kVA to be able to be delivered by your first existing transformer. That's this one over here. And so then you're going to go and put on a new transformer. You want to parallel it onto the same bus. In other words, you want to go and connect it to the same high and connect it to the same low. What this drawing over here is showing is that we can parallel up any type of transformer, provided that we go and do it practically. We can go and stick an additive polarity onto here. So over here I've got an additive. Remember, it's like the addition mark. It crosses over itself. So here's my existing one that I have over here that I'm going to go and parallel up with another additive one. All that I'm noting is that my X1s are connected to all the same lines. My H1s are connected to all the same lines inside of here. The next example down shows that we can have a subtractive. Here's my H1, here's my H1, they're connected to the same lines. Here's my X1s, here's my X1s, they're connected to the same lines over here as well. So we can parallel another subtractive on. Alternatively, if we already have an additive on here, we can parallel on a subtractive. All that we're going to have to do is we're going to have to watch our transformer polarity. If I've got the H1 connected to this line, H1 connected to this line, I'm going to just play matchy-matchy. That's all we're doing. It's like kindergarten games. Just match it. Does this line have the X1 connected to it? Perfect. Connect your X1 to it, and you cannot go wrong off of it. So we want to be able to go and do these applications, paralleling up transformers. A couple of reasons. Sometimes it's going to be that we're adding onto a system. Other times, it can simply be the pragmatic approach of, if I get myself a massive single transformer on there, that huge single transformer might not fit through the door of this electrical room. Somebody screwed up on the planning, the engineers for the electrical didn't talk to the architectural, and all of a sudden they come to these cases where there's like, well, you told me that this is the electrical room, but you only gave me a 32-inch door, and it's got support columns on either side, so we can't cut into it. What are we going to do? It's something that actually happens. I've run into problems like that before, working for a company years back, where they had an entire MCC bus system that they had to take apart and take in through a small door because the engineers hadn't gone and spec'd a large enough door on the electrical room. So sometimes what you'll end up doing is you'll be taking in two smaller ones because you can fit them in there, or because you can lift them, you can mount them on the walls or something like that. And so it just becomes this thing where it makes more sense to use two smaller components for the physics of it, the actual physical size. In order to be able to go and safely do this, we do have to go back through these other steps. We have to go and meet a couple of conditions. The first condition that they give us is that the transformers must have the same primary and secondary voltage ratings. This makes sense because really we're paralleling together a couple of different power sources. And if I go and have this one here that's going to be, let's say, 120 volts, and I have this one here that's 120 volts, is there going to be any potential difference between this and this? No. Therefore, is there going to be any current flow between this point and this point? Absolutely not. But then if I go and place this one on here, and this one got a value of 110, is there any potential difference between this and this? Absolutely. There is 10 volts of potential difference. And so the bigger one is going to go and bully the smaller one. That's what happens inside of these electrical circuits. The bigger one is always going to go and win. It's got more force. And so it is going to go and force current through. It's going to go and take the smaller one. It's going to treat it like a load. In other words, it is going to deliver some of its current through this one over here. Same with this one over here. It's also going to go and gang up on this one. They're going to be delivering current through there. This would be a bad thing. Now, if we're looking at batteries like this, yeah, you recharge some types of batteries are going to be fine, but it's not going to be a healthy thing. It's also unnecessary amounts of current. If it were a transformer, we're going to go and have net amounts of current that are then going to be counteracted. It starts to really screw around with a lot of our counter EMFs as well. They give us these examples over here where they're showing us, batteries with unequal voltages that are going to be placed in parallel. You'll note that once again, we've got our larger one that is going to treat our smaller one as if it were a load. Both of these are going to be delivering out a grand total of 22 to our loads over here, or 24 to our loads here, but we are going to go and have a circulating current that's going to go in between these two. They show a little formula underneath there. This diagram over here, really what the formula is they're taking the volts difference divided by the resistance of these actual components, 0.25 of the ohms, the resistance of the path that they are going to go and have. And that's going to go and tell them the size of the circulating current. In this case, it's not a huge circulating current, it's 4 amps, but it's still going to go and cause some problems inside of here. When we have transformers, our transformers are going to be built by different manufacturers. There's a ton of different ones out there. You got your big names, Hammond and Rexel and some of these ones, but you're also going to have a lot of other smaller companies that can wind these transformers, and when they do so, they're going to have different percent impedances. We haven't covered what percent impedance is or how to calculate it, but we're going to find out that there's a small resistive value associated with each. If these resistive values are different, what's going to happen is we're going to drop our values of voltage out of these things different. So what I'll do is I'm going to take this same one over here. This one's not inside the book. We're just going to show how the percent impedance is going to go and change what happens inside of our inside of here. So percent impedance is really going to be a voltage drop that we are going to go and have inside of here. What I'm going to do is I'm going to go and take this. I'm going to go and say that this is actually a proper 24 volts. Okay, we're going to change this. Right now we're looking at the percent impedance and how it develops problems. This is going to be 24 volts, but what I'm going to do is I'm going to change this. Instead of having an internal impedance of 0.25 of an ohm, I'm going to go and change this thing to a 0.5 of an ohm that I'm going to go and have. What do we get? Well, we've got 24 volts that is going out, and it's going to go across this 0.5 of an ohm. Over here, I got 24 volts over top of 0.25 of an ohm over here. And so what I'm going to get now is I'm going to get a differing amount of voltage drop. Let's start by putting a resistance over here on the load. It doesn't matter what that resistance is going to go and be, but let's start by saying that this is going to be a 6 amp load. It's probably easiest to work with the current. We don't need to go through the resistance, we just need to look at the current. If I've got 6 amp, what I should have is I should have 3 amps fed out of here, and I should have 3 amps that are going to go and be fed out of here, right? Kirchhoff's law of current. The two currents entering the node should be the same if they're from the same size of supply heading out that way. However, it's not going to work out quite like this, because if I take a look at this, this is 24 volts, 0.5 of an ohm. V is equal to I times R. So if I take a look at 3 amps traveling through 0.5 of an ohm over here, what that's going to do is it's going to give me a voltage drop of 1.5 volts that I'm going to go and have before I even leave this transformer winding. It's the DC equivalent that we're drawing here. This one over here, I've got 3 amps, and that 3 amps is passing through here. V is equal to I times R off of this one here. So now I'm going to go and have 0.75 of a volt that I'm going to go and drop 0.75. Which means that the ultimate total terminal voltage of these two supplies is going to be different. This is going to be 24 minus 0.25, so it's going to be 23.25. This one over here is going to be 24 minus 1.5, which means that it is going to go and be 22.5. So differing percent impedances lead us back to this same original problem that we had, which is going to be that now we are going to go and have unequal voltages. And as soon as we've got unequal voltages, because the internal impedance of one of these is high enough, then it's going to lead us to having circulating currents between these two as well. I'm not going to draw on the circulating current. It's going to be done the same way. The voltage differential over top of the amount of resistance. So we do need to have the same percent impedances. Last thing that we need to have is obviously we need to connect them to the same polarity. This kind of just makes sense. If I connect, the positive, the instantaneous positive, the X1 on one transformer, I need to connect the X1 on the other transformer to the same line. If not, we end up with this, which is going to be a massive problem where we'll call this my X1, we'll call this my X1 of the other one, where we start to see now that we are going to go and have a massive circulating current that's going to be going through these ones over here. It's basically going to be the sum of these two voltages, 24 plus 24, so 48, over top of half of an ohm, 0.25 plus 0.25, which means that we will end up with a large amount of current, 96 amps, they calculate out of these ones. Okay, so going back to these ones, what we should have for all three of these is that they're going to have equal voltages. They should have equal percent impedances that they're each going to go and have, and they should be matched polarities. Not that they're subtractive and additive, but just that I'm going to polarity matched, that I'm going to go and make sure that always my X1s are connected to the same line. X1s connected to the same line, X1s connected to the same line over here. Okay, when we do these tests, there is a way to double check to make sure that we've done it correct. One of the ways to do it is to do what's called a voltmeter closure test. And a voltmeter closure test is really where I'm going to go and hold off on doing my final connection. And I'm going to go and check my value of voltage with a voltmeter first. And then if it looks good, then I will go and close in. If not, I'm not going to bother closing in. I'm going to go and reassess what I've done over there and whether or not it is a good type of system. The voltmeter closure test is going to be us taking a look at a partially done connection, and this is just going to be our last connection that we're checking over here. Same as what we just said there before. If my connection is correct, in other words, if I've got all the polarities lined up off of here, what I will see is I should see 0-ish volts that I'm going to go and have. If I have got improper polarity, what I'm going to go and see is double the value of voltage that is going to go and be. Now, practically speaking, there is going to be a little bit of induction, and we are going to go and see some small differentials. But we are going to be able to identify, for sure when we've got a bad connection. Anything that is not a full bad connection, we can assume then would have to be the good type of connection. Over here, they're showing us the voltmeter closure test on a partially done bank. We're going to go and take this voltmeter out right now, and we're going to go and take a look at what's actually happening inside of here. We've got this one over here. We're going to call this one our existing one that we have. The existing one has an H1. It has got an X1 over here. I have got it connected. Now there's instantaneous polarities shown over here, but they are not going to stay there. As AC, they do change. What I have got over here on this side is my new transformer. Now what I'm going to do is I'm going to hook up my new transformer. So I'm going to go and have my H1 and my H2. I'm going to go and match them, right? I trace of the line that's got H2 connected to it. I connect my H2 to it. Trace of the line that's got my H1 connected to it. I connect my H1 to it. Then what I'm going to do is I'm going to go and partially complete my bottom one. You can partially complete it because at this point it's nothing more than a stinger coming out of the circuit. It has no complete path for current flow through it. Therefore, it cannot cause a problem if it is screwed up. So I've connected onto it. Let's say that, we didn't know for sure which one was X1 or X2. We just know that we had our low voltage side over here because, I don't know, those winding markings disappeared or something like that. What I'll do is I'll make one connection on over here, and then what I'm going to do now is I'm going to go and insert my voltmeter. I'm going to power up the system. So everything would have been disconnected up until now. Now I'm going to go and turn my system on, and I'm going to take my voltmeter and I'm going to go and measure from here over to the last line that it should be making connection, right? We understand that it should be making connection to this one. We would not want to connect to that line because we already got a line on there. There'd be no potential difference. It wouldn't make any sense. So I'm going to go and take my voltmeter. I'm going to place it across from here to here. And then I'm going to read what's on that voltmeter. What we should have is we should have a value of approximately 0 volts that's going to be across there. Theoretically, it should be 0. Now, there will be small amounts of induction and circulating currents inside of here. It will be picking up a little bit of current off here, inducing a little bit of voltage. So in reality, it's going to be 0 to maybe up to about maybe half of the rated amount of voltage. If this is supposed to be a 120 volt bus, we can get up to from maybe 0 to 60 volts or something like that. You might see some voltage on it, and that's perfectly fine because that's just assumed to be what we refer to as magnetizing current. What we don't want to see would be the second case over here. Second case over here is the same setup. We've got a transformer that we are paralleling in, but we don't know whether or not we've got that connection done correctly. We've connected on our high side, so here's my existing. Here's my new one that I'm putting in. I connect my H1s on my high side. I connect my H2 to the opposite line, so the H2s are matched. Then I take one of my lines and I connect them onto something. We don't know which line it is yet, so we've got it connected to one of these lines over here. And then the last step is going to be me taking my voltmeter out once again and then going from here over to, oops, sorry, the wrong line there. Going from here over, oh no, over to my other line. All right, hold on. I'm just going to go and pull that one back up again. It really doesn't like this PowerPoint. I have no idea why. I will have lost all of my lines, but it will only take us 2 seconds to get back to where we were. All right. So we're going to be measuring with our voltmeter at this point, and we're checking what our value of voltage is. If it is improperly done, what I will have done at that point is I'm going to have created a 240 or a 2x the voltage, double the voltage. If this was a 120 volt system we were paralleling onto, I'm going to have 240. If it was a 240 volt system, I would see 480, but I'm going to see a doubling of the voltage. That is going to go and tell me that I've got a bad type of connection. I should have, if it was a good connection, between 0 to about half voltage at the max. But this is terrible form. Okay, we don't want to go and see this where we're going to have double voltage. That's why we do this test, is just to verify. Because if I bolt all these connections together and then I were to go and power this system on, let's say that I didn't do this test because, I'm pretty confident in what I'm doing. I am actually overly confident a lot of times. It's caused problems before in the past. Don't ask questions. Just know that it does. But if it does, what I would see over here is that I'm going to go and have current that is going to go and circulate in this path. We've got that shorted out type of path. Really, when you take a look at it, what we're doing inside of here is not a whole lot different than when we had those double connections. Wait, where are they? No, not that one. One further up. Over here. Really, it's not a whole lot different than what we were doing before, where we were just making sure that we didn't have these improper transformer connections shown inside of here. The connection that we have made right now is actually entirely equivalent to this one that they had over there, but we're just making it using now 2 transformers that are single winding instead of, 2 single transformer that's double winding inside of there. It's going to be a terrible, terrible value of voltage to go and have. So I'm going to go and disconnect. If I'm reading that high amount of voltage, we disconnect that. We then go and reverse the connection. And then we are going to go and once again do the voltmeter closure test. Okay, voltmeter closure. You can remember the whole thing as 0 to about half voltage, probably good. Double voltage, 100% bad. Guaranteed that that thing is going to be bad. It might even be a little more than double the voltage because it's going to go and have, once again, those magnetizing currents. If I'm doing a 3-wire transformer that I'm paralleling on, I'm going to have to do 2 voltmeter closure tests. I'm going to want to double check both of them. Now, in reality, if I do one test and it checks out all right, the other one should be all right as well. But it's best case always to go and double check these. Well, let's go and change this transformer that we have over here as well. Because where this gets a little bit more confusing is when we have got a transformer that doesn't have all the same terminals. Like over here, we got this, X1 and 2 to 3 to 4 like that. But in some cases, what we might do is we might just have a transformer that looks like this, where it's got an XO, and this one here has got an X2 that is going to be off of it. In that case, same deal. We're going to connect our neutral in to the same point that we have our neutral over here. This is a split winding. This is one that's got a manufactured neutral inside of it. And then I'm going to go and take a measurement before I make the closure. This is an open connection on both of these right now, and I'm just going to take a measurement across the line that I think that they should be going over to and double check them like that. Once again, what's my value of voltage going to be? It's going to be double what I am going to be reading across here. If this one was a bad one, it should be double of 120, right? Because it's going only across from this coil to this coil over here. That's only 120 volts that we would see across there. So we should never see anything other than 240 volts or, maybe up to about 60 volts off of it. It's always going to be measuring the phase value that we're going to be doing the closure test on. All right. Last section that we got to talk about over here when we're dealing with paralleling is the fact that we can go and have transformer backfeed hazards. We have not talked about transformer disconnections, but the Canadian Electrical Code is very strict about what we must do with every transformer. You should be already familiar with where you're going to find the bulk of your transformer problems inside of the Canadian Electrical Code. Those are going to be inside of your section 26. 26 is our installation of electrical equipment. Transformers are a definite type of electrical equipment. Most of our rules are going to be found inside of here. We've got a couple others that are spread throughout, like grounding and bonding, as well as through some of our high voltage sections, but the bulk are going to be found inside of here. There's going to go and be a number of rules laid out that are going to be general. Oop, I went up one there by accident. There's going to be general ones that are going to go and talk about what the transformers are going to be. Dielectric ones, anytime that we see dielectric liquid filled, that's going to be talking about oil-filled types of transformers. How we have to go and mount them. There's also going to be inside of section 26 at the very front of section 26. Let's just scroll up there over there. There's going to go and be a complete separate section that talks about dielectric liquid-filled equipment that's indoors or outdoors. So we might have to go and refer to some of these as well for some of our transformers. But going back down into the transformers itself, transformers mounted on roofs. Then we've got dry core, open ventilated type transformers. This is going to be the ones that we most commonly use inside of our electrical rooms. It's going to be a rule that is going to be highly useful to us. This talks about the installation, how we are going to go and place them in. Then we're going to go and have this rule here, which is the big one that we wanted to get to, disconnecting means. And it says that the disconnecting means shall be installed in the primary or the infeeding side of each power and distribution transformer. Note that they say power and distribution. They don't say control transformer and they don't say signaling transformer. We don't need to always have them inside of those, but inside of anything that is a power and distribution, we do. And the reason that we need that is simply because we need to be able to go and isolate, particularly for this transformer backfeed hazard. Do transformers work in both directions? Absolutely, transformers do work in both directions, which means that I can feed a low voltage in and get a high voltage out, or I can feed a high voltage in and get a low voltage out. Now, normally speaking, what I would have inside of here, if this switch was closed, I would have these two transformers that would be operating in parallel, which would both be supplying power out to this secondary bus, right? We would be taking power in on the primary bus, supplying it out to the secondary bus. Let's say that for whatever reason, we have got to go and work on this transformer. Now, what we do, we've all gone through safety stuff in first year. We know that what we need to do is we need to do this whole lockout tagout thing, right? Where we're going to go to this thing, we're going to open it, we are then going to go and lock it out, then we are going to go and test for power, and then we're going to go and work on it. Unfortunately, not everybody in the trade follows this. People just throw switches and they're like, yeah, it's good to go, I'm going to jump on this thing, and then boom! They just get fried by, 12,000 volts in this case of electricity because they have not gone through the whole lockout tagout. This backfeed hazard is not a hazard if you are following lockout, tagout, and testing. Just do it, okay? It sucks to get high voltage shocks. I've had them before. But if you're not, you run yourself this risk because what we have over here is we've got this transformer that somebody's thrown this disconnect on, and now they're just going to go and jump into that transformer and start, cleaning or adjusting or whatever. But there's still this path for current. What we have is we still got current that is passing into this transformer as electricity. It is then going to go and get converted into magnetism, pass through into this side where it is going to generate electricity. That electricity is then going to go and pass into this side here where it's going to generate magnetism. Those electromagnetic lines of flux are going to cut across to this side here where we have that good old Faraday's EG is equal to BLV. And so we have got generated value of voltage, and it's going to be generated off the fact that this transformer is going to be seeing full voltage because that's being fed out of here. Therefore, it's going to have full flux. Therefore, it's going to stick out full 12 kV that is going to be across here. Anytime that you are going to be working on a parallel transformer, you need to understand that this hazard exists. Now, the Canadian Electrical Code only has requirements that we place a disconnect. That same rule that we were just looking at there, 26248, says that we have to have a disconnect means in the primary of our circuit. It says nothing about needing to have one inside of the secondary. However, on paralleled transformers, if there is a chance that you are going to be doing transformer servicing on a lot of our high voltage systems, you have to do periodic servicing because the bushing, that's going to be the high voltage connection on the top, it's that ceramic thing, kind of looks like a... It's got all these rings that are there for drip cap. I'm drawing this thing very poorly, but I think you know what I'm talking about. It's a big white ceramic bushing usually, and then it's going to go and have a stud on the top, and then this is where it's actually going to attach onto there. These are high voltage bushings. If we build up dust and debris and stuff like that, it leads to problems with what's called tracking. And tracking is where we're going to go and have high voltage electricity that's going to go over top of the surface of it, and then go and hit the can, which is going to be bonded down to ground. So we've got a complete separate industry. There's a complete separate industry of electricians. One of my old co-workers works in that now, and he calls himself a high voltage maid. They go to places that are high voltage, they do a shutdown, and they go and clean them. Special cleaners, you can't just go throw like Windex on stuff or anything. You have to make sure it's not going to be corrosive to the equipment or the cable linings or anything like that. But they go and clean all this stuff off, and so they have to go and shut off. They'll still maintain power to the plant. They'll be operating at a reduced capacity because they've only got one of the transformers going. But before they can get in here and clean this, they need to go and disconnect. So if you've got high voltage setups like this, you're very commonly going to go and have a second disconnect in the secondary of each transformer. Okay? Not always needed, but if you're paralleling, it's very good form to have a second one on there, because now what I would be able to do is I would be able to keep this one closed. I should close that one. Like that. I would be able to open this one. When I open this one, that transformer backfeed hazard doesn't exist because the electricity can't get through to here to flux the core to go and flux this side. Therefore, this would no longer be at 12 volts or 12 kV. This would be 0 volts that I would have off of it. Watch out. Be very, very careful with transformer backfeeds, and be very careful with what you allow a customer to backfeed as well. This is a huge concern to BC Hydro. If BC Hydro finds out that you are backfeeding onto your panel, this is why we've got transfer switches that disconnects us from Hydro when we go and operate a generator. There's this huge danger where people make those like double-ended extension cord where they stick 2 male ends on an extension cord. Then they plug one into the generator, they plug one back into their house, and they'll backfeed their house, as they call it. What's actually happening is, unless they've thrown the main breaker, they're going to be backfeeding the neighborhood transformer as well. And when Hydro comes around to go and fix whatever that problem is, those Hydro linemen can go and get a shock off that. They will track that down pretty dang quick, and they just do it just by cutting off people's connections until they get rid of that connection. They'll remake the connections for everybody that wasn't backfeeding the system, but the poor sap that was backfeeding the system, they're going to have to wait a long time and deal with a lot of paperwork before BC Hydro is going to go and give them power back. All right, just be careful in your own operation that you do not get bit by this backfeed thing.